Tonight, we're going to do something different. We're going to talk about a world that almost no one talks about when they talk about humanity's future in space. Not Mars, not the Moon, not the asteroid belt or the cloud cities of Venus. Tonight, we're going to talk about Titan, the largest moon of Saturn, a frozen world wrapped in a thick orange haze, with rivers of liquid methane running across its surface and an atmosphere denser than Earth's. And we're going to talk about why colonizing it might one day become the most painful decision humanity has ever made. You may have heard whispers of Titan in the last few years. Planetary scientists keep returning to it in their papers. Engineers keep slipping it into long-term mission proposals. A small but growing chorus of physicists has begun to argue, very quietly, that Titan, not Mars, is the real destination, the place where humans could actually live. The place where a self-sufficient settlement could survive for centuries. And once you understand the numbers, the chemistry, the physics, the strange and beautiful environment that exists more than 800 million miles from the Sun, it becomes very difficult to argue against them. Titan, on paper, is the most habitable world in the solar system outside of Earth itself. That is what makes the decision so painful, because Titan also represents a kind of finality that Mars does not. A distance so vast, a journey so long, an environment so utterly alien that everyone who goes will not only never return, they will never even be reachable in any meaningful sense. They will pass beyond the edge of human civilization, into a place where light from Earth takes more than an hour to arrive, where rescue is not difficult but mathematically absurd, where the people back home will essentially be living in a different century by the time messages cross the gap. To choose Titan is not just to choose exile. It is to choose to step outside of human history altogether and to begin writing a new one in the dark. Before we go any further, if this kind of slow, immersive exploration of space and the future is the sort of thing that keeps you up at night in a good way, take a moment to like the video or subscribe to the channel. It costs you nothing, and it helps these long, careful conversations reach the people who genuinely want them. Now, let's continue. The idea of going to Titan sounds, on first hearing, ridiculous. Saturn is the sixth planet from the Sun. Its average distance from Earth is roughly 890 million miles, and depending on where the two planets are in their orbits, that distance can swell to over 1 billion miles or shrink to about 750 million. To put that in perspective, Mars at its closest is 34 million miles away. Titan, even at its closest, is more than 20 times farther. The Cassini spacecraft, which spent more than a decade studying Saturn and its moons, took nearly 7 years to get there, and that was using a complex gravity assist trajectory that flung it past Venus twice and Earth once and Jupiter once just to gain enough velocity to reach the outer solar system. A direct trip with current chemical propulsion would take 6 to 8 years one way. A faster trip, using technologies that don't yet exist in operational form, might be cut to 3 or 4 years. But there is no version of this journey that takes months. There is no version that takes a single year. The journey to Titan is measured in the slow, grinding accumulation of years. And yet, scientists keep coming back to it. They keep running the numbers. They keep proposing missions. They keep writing papers with titles like Titan as the long-term destination for human settlement, and why Saturn's largest moon may be humanity's most realistic second home. Because once you arrive at Titan, something strange happens. The numbers, which look so bleak from a distance, begin to flip. The math that makes Mars a slow death starts to bend in your favor. The physics that turns the moon into a radiation hazard and Venus into a furnace begins to whisper, quietly, that Titan might be a place where humans could actually walk outside without a pressure suit, could fly with strapped-on wings, could build cities under domes that don't need to be reinforced against vacuum, because there is no vacuum, just a sky full of nitrogen and methane, denser than the air at sea level on Earth. This is the paradox we are going to spend the next 14 sections unraveling. The contradiction at the heart of Titan. Why this distant, frozen, hydrocarbon-drenched moon is simultaneously the most welcoming world we know of beyond Earth, and the most agonizing one to commit to. Why every advantage Titan offers comes paired with a cost so steep, so permanent, that that the people who choose to go will be making a decision that no other generation of humans has ever had to make. Not the Polynesians who crossed the Pacific, not the Europeans who sailed for the Americas, not the Mars colonists who, painful as their decision is, will at least look up at night and see the same sun, the same recognizable star patterns, the same familiar light. The first Titans, by which I mean the first humans to live on Titan, will look up and see a sky filled with orange, haze so thick that the sun itself will appear only as a dim, faintly glowing patch, no brighter than a full moon on Earth. They will live in twilight, permanent, golden, suffocating twilight, and they will know every single day that this is the sky their grandchildren will know as home. That is what we are going to explore tonight. Not just the engineering challenges, though we will go deep into those. Not just the propulsion problems, the life support questions, the radiation calculations, the energy budgets. We are going to talk about the human cost of crossing that gap, the mathematics of distance and the mathematics of grief, the way the human mind processes permanence, the slow erosion that happens when communication with home takes hours and the people you love age into strangers between exchanges of messages. We are going to talk about why some of the most respected planetary scientists in the world are starting to look at Titan and say, this is where humanity goes to outlast itself. And we are going to talk about why even they admit, in quiet moments, that the people who go will pay a price no one can fully prepare them for. Stay with me. This is a long journey, fitting given the subject, because before we can understand why Titan colonization is the most painful decision humanity could ever make, we need to understand how this distant, ringed planet moon came to be considered in the first place. And for that, we have to travel back through the centuries, to the night a Dutch astronomer pointed his telescope at Saturn and saw something he could not explain. The story of Titan begins on a cold March night in 1655 in the small Dutch city of The Hague. A young astronomer named Christiaan Huygens, only 26 years old at the time, was experimenting with a new telescope he had built with his older brother Constantijn. The Huygens brothers were not just observers. They were craftsmen, lens grinders, optical theorists, and they had developed a method of polishing telescope lenses that produced sharper images than anything previously available in Europe. Christiaan had been pointing this new instrument at Saturn for weeks, fascinated by the planet's strange, ear-like appendages, which Galileo had glimpsed 40 years earlier but never been able to resolve clearly. On that particular night, while studying Saturn, Christiaan noticed something he had not seen before. A small, steady point of light sitting just to the side of the planet. It did not flicker like a star. It did not drift in the wrong direction like a chance alignment. Over the following nights, he watched it move, and he realized slowly, with the quiet shock that great discoveries always carry, that he was looking at a moon orbiting Saturn. The first moon ever discovered around any planet other than Earth or Jupiter. He called it, simply, Saturni Luna, Saturn's moon. The name Titan would come later, given by John Herschel in the 19th century, drawn from Greek mythology, the Titans being the elder gods who came before the Olympians, the primordial beings of immense power who ruled before Zeus and his siblings overthrew them. It was a fitting name for a moon that would turn out to be larger than the planet Mercury, larger than every moon in the solar system except Jupiter's Ganymede, a world so substantial that if it orbited the Sun directly instead of Saturn, we would call it a planet without hesitation. For nearly 3 centuries after Huygens, Titan was little more than a point of light to astronomers. They knew it existed. They knew it was large. They could measure its orbit around Saturn with increasing precision, but they could not see its surface. They could not even tell if it had one. In 1908, the Spanish astronomer Josep Comas Solà reported something extraordinary. He claimed to have detected a thin atmosphere around Titan, observed as a darkening at the edges of the moon's disk through his telescope. It was a controversial claim at the time. Other astronomers were skeptical. But by 1944, the Dutch-American astronomer Gerard Kuiper confirmed it definitively using spectroscopic analysis. Titan had an atmosphere, and not just any atmosphere. Kuiper detected methane, the same hydrocarbon gas that on Earth is associated with swamps, with cattle, with the decomposition of organic matter, with the deep stirrings of biological activity. This was the discovery that changed everything. Because up until that point, the conventional wisdom held that moons could not have atmospheres. They were too small. Their gravity was too weak. Any gases they once possessed had long since drifted away into space. The fact that Titan had retained a thick atmosphere billions of years after its formation suggested that Titan was something special, something fundamentally different from the dead, airless moons of Jupiter, of Earth, of Mars. Titan was a world. A real world with weather, with chemistry, with the slow churning of an active environment. And the presence of methane raised a question that scientists would chase for the next 80 years. Where was the methane coming from? Because methane, exposed to ultraviolet light from the sun, breaks down. It does not last. The methane in Titan's atmosphere should have been destroyed by now. The fact that it was still there meant something was replenishing it. Something on Titan, or beneath Titan, was producing methane continuously, and that something might just possibly be alive. The space age finally gave us our first close look. In November of 1980, NASA's Voyager 1 spacecraft, on its grand tour of the outer solar system, swung past Saturn and made a deliberate course adjustment to fly within 4,000 miles of Titan. It was the closest any human-made object had ever come to the moon, and the scientists at the Jet Propulsion Laboratory in California waited anxiously for the images to come back. What they saw was disappointing, and also, in its own way, mesmerizing. Titan was completely shrouded in an orange-brown haze. No surface features were visible. No mountains, no valleys, no craters, no oceans. Just a smooth, featureless ball wrapped in a dense, opaque sky. Voyager 1 had given us our first close look at Titan, and Titan had refused to show its face. But Voyager did give us numbers. Real numbers, measured directly, that transformed our understanding. Titan's atmosphere was not just present, it was thick. Surface atmospheric pressure on Titan turned out to be 1.5 times that of Earth at sea level. The atmosphere was composed mostly of nitrogen, just like Earth's, with a few % methane and traces of other hydrocarbons. The surface temperature was a brutal -290 degrees Fahrenheit, and the atmosphere extended upward for hundreds of miles, far thicker proportionally than Earth's own. Titan, Voyager confirmed, was the only moon in the solar system with a substantial atmosphere, and it was unlike any other world we had ever encountered. The real revelation came 25 years later. In January of 2005, a small probe named Huygens, named in honor of the moon's discoverer, separated from the Cassini spacecraft, which had arrived at Saturn the previous year, and began a slow parachute descent through Titan's atmosphere. For 2 hours and 27 minutes, Huygens fell through the orange haze, transmitting data the entire way. Then it landed, intact, on Titan's surface, becoming the first human-made object ever to touch down on a world in the outer solar system. The images it sent back were extraordinary. They showed a landscape that looked eerily like Earth. There were pebbles scattered across a flat plain, smoothed and rounded by some kind of erosion. There were channels carved into the terrain, branching tributaries that looked exactly like dried riverbeds. There was a hazy orange sky overhead. It was, the scientists realized with growing astonishment, a world that had weather. A world where liquid flowed across the surface, carving valleys, smoothing stones, depositing sediments. Not water. Water on Titan is frozen as hard as rock. The liquid was methane and ethane, hydrocarbons that on Earth exist as gases, but on Titan, at those frigid temperatures, condense into rain and fall from the sky and pool into lakes and run in rivers. Cassini, orbiting above, mapped these features in detail over the following decade. There were lakes the size of the Great Lakes of North America, filled with liquid methane. There were vast dune fields made of hydrocarbon sand. There were mountains, cryovolcanoes, possible subsurface oceans of liquid water beneath the icy crust. Titan was not a frozen, dead moon. It was a living, breathing, weather-driven world with a hydrological cycle every bit as complex as Earth's, just running on different chemistry. And it was this realization, slowly building over decades of observation, that changed how planetary scientists thought about humanity's future in space. Mars had been the obsession. Mars had been the dream. But Mars, for all its romance, was a thin-atmosphered, radiation-bombarded desert. Titan was something else entirely. Titan had a sky. Titan had pressure. Titan had chemistry. Titan, in some quiet, almost embarrassing way, was beginning to look like the most welcoming place in the solar system that wasn't Earth. The question was no longer whether Titan could be reached. The question was whether anyone who reached it could ever bear to come home. For most of the late 20th century, conventional wisdom in the space community held a single, almost unquestioned belief about humanity's future beyond Earth. Mars was the destination. Mars was the goal. Mars was where we would go first, where we would build our first off-world settlement, where we would prove that humans could become a multi-planet species. Everything else was secondary. The moon was a stepping stone. The asteroid belt was an industrial opportunity. The outer solar system was a place for robotic probes, beautiful and distant, and forever beyond human reach. Mars was the only realistic candidate for human colonization, and the entire architecture of space planning, from NASA's roadmaps to SpaceX's mission designs to the private sector's investment patterns, was built around this assumption. The reasoning seemed airtight. Mars was close. Mars had a day-night cycle similar to Earth's. Mars had ice. Mars had a thin atmosphere that, while unbreathable, provided at least some protection from micrometeorites. Mars had gravity that, while only 38% of Earth's, was at least gravity, not the disorienting weightlessness of space stations or the crushing pull of the gas giants. Mars was where you went if you wanted to plant a flag on another world and have any reasonable hope of building a base there. Every major space agency, every serious commercial spaceflight company, every academic institution studying human factors in space agreed. Mars first. Mars now. Mars next. The arguments against considering anywhere else were practical and, on the surface, persuasive. The moon was too small, too airless, too radiation-soaked, with a day-night cycle of 2 weeks of brutal sunlight followed by 2 weeks of crushing cold. Venus was a furnace, with surface temperatures hot enough to melt zinc and atmospheric pressure equivalent to being a half-mile underwater. Mercury was even worse, a cratered rock with no atmosphere, baking on its sun-facing side and freezing on its dark side. The asteroid belt offered no gravity worth mentioning, no atmosphere, no protection. And the outer solar system, the realm of Jupiter and Saturn and beyond, was simply too far, too cold, too distant from the sun for solar power to function effectively. Too long a journey for human bodies to endure. Everyone agreed on this. Mars was the answer. The conversation was settled. But beneath this surface consensus, something strange was happening in the quieter corners of planetary science. Researchers who had spent decades studying the data from Voyager and Cassini, who had pored over the atmospheric chemistry and the surface imagery and the gravitational measurements, were beginning to ask uncomfortable questions about whether the conventional wisdom was actually right. They were running calculations that the mainstream did not want to acknowledge. They were comparing Mars to Titan, point by point, on the metrics that actually mattered for long-term human habitation. And what they were finding was deeply unsettling for anyone who had built a career on the assumption that Mars was the answer. Consider radiation. On Mars, the atmosphere is so thin, about 1% the density of Earth's at sea level, that it provides almost no protection against cosmic rays or solar particle events. A human standing on the Martian surface would receive a radiation dose roughly 50 times higher than on Earth. Over the course of a multi-year stay, this exposure becomes a cancer risk so severe that NASA's own studies have concluded astronauts would exceed their lifetime radiation limits during a single mission. To protect colonists on Mars, you would have to bury habitats under several meters of regolith, or build them inside lava tubes, or shield them with water tanks. Living on the Martian surface, walking outside in a suit, conducting any extended activity in the open, would be slowly lethal. On Titan, by contrast, the atmosphere is so thick that it provides radiation shielding equivalent to several meters of solid material. Titan's atmosphere blocks cosmic rays nearly as effectively as Earth's. A human standing on Titan's surface would receive a radiation dose comparable to what we receive on Earth at sea level. This is not a small advantage. This is a fundamental difference in habitability. Mars is a radiation hazard that requires constant engineering effort to mitigate. Titan is naturally shielded by its own atmosphere, no engineering required. Consider pressure. On Mars, the atmospheric pressure is about 1% of Earth's, which is essentially a vacuum from a human survival perspective. If your habitat depressurizes, you have seconds to find a suit before your blood begins to boil. Every structure on Mars must be a pressure vessel, engineered to withstand the difference between internal Earth-like pressure and external near vacuum. This is a massive engineering challenge that affects every building, every airlock, every vehicle, every piece of equipment on the surface. On Titan, the atmospheric pressure is 1.5 times that of Earth at sea level. This is the pressure equivalent of being in a swimming pool about 15 feet down. Human bodies can tolerate this pressure without difficulty. More importantly, your habitat does not need to be a pressure vessel in any meaningful sense. The pressure inside and outside is roughly equal. You can build structures on Titan using techniques that resemble Earth construction far more than anything that would work on Mars or the Moon. A torn habitat wall on Mars is a death sentence. A torn habitat wall on Titan is an inconvenience. Consider temperature. Yes, Titan is brutally cold, around -290 degrees Fahrenheit on the surface. This is colder than anywhere on Mars by a wide margin. But here is the strange truth about cold versus radiation versus pressure. Cold is the easiest of those three problems to solve. Insulation works. Heating systems work. The thick atmosphere on Titan actually helps, because while it conducts some heat away from a habitat, it also dampens temperature swings the way Earth's atmosphere does, preventing the wild thermal cycling that occurs on Mars and the Moon. On Mars, temperatures can swing by more than 150 degrees between day and night, which creates enormous stress on materials and equipment. On Titan, temperatures are stable. Cold, yes, but predictable, with relatively small variations. From an engineering perspective, designing for steady cold is far easier than designing for thermal cycling combined with vacuum combined with radiation. Consider resources. Mars has water ice. This is the resource everyone talks about because water can be split into hydrogen and oxygen for fuel and breathing. But Mars has very little else that is directly useful for human survival. The soil is full of perchlorates, toxic chemicals that contaminate any water extracted from it and pose serious health risks if inhaled as dust. The atmosphere is mostly carbon dioxide, which is useful for fuel production but useless for breathing. Titan, by contrast, has water ice in vast quantities, frozen as hard as rock and forming most of the crust beneath the hydrocarbon surface deposits. Titan has methane and ethane lakes that represent an essentially unlimited supply of hydrocarbons for fuel and chemistry. Titan has nitrogen, which makes up most of its atmosphere and which is essential for any closed-loop life support system and for fertilizing crops. Titan has, in short, all the elements needed for organic chemistry sitting on its surface in industrial quantities. The picture that emerged from these comparisons was startling. On almost every metric that mattered for long-term human survival, with the single significant exception of distance from Earth, Titan was a better candidate than Mars. The atmosphere was better. The pressure was better. The radiation environment was better. The resource availability was better. The only thing Mars had going for it was that it was closer. And that, the quiet voices in planetary science were beginning to argue, might not be the most important factor when you were talking about a settlement intended to last for centuries. But conventional wisdom is a powerful force. The Mars First narrative had momentum. It had funding. It had decades of mission planning behind it. And so the case for Titan remained, for years, a fringe argument, whispered at conferences, published in obscure journals, dismissed by the mainstream as romantic and impractical, until something happened that would force a reckoning. The first cracks in the Mars First consensus did not come from a single dramatic announcement. There was no press conference, no headline-grabbing paper, no public declaration that the entire field had been wrong. The shift was quieter than that, slower than that, and in some ways more unsettling because of it. It happened in conference rooms, and in late-night conversations between researchers who had been working on Mars mission designs for decades. It happened when engineers ran the numbers one more time and came up with answers they did not want to share. It happened when the cumulative weight of small problems began to look, when you stepped back, like one very large problem that no one had been willing to name. The first crack was the dust. For years, NASA's rovers had been sending back data about the Martian regolith, the fine-grained soil that covers the planet's surface, and the data was disturbing. Martian dust is not like Earth dust. It is electrostatically charged, meaning it clings to everything, to suits, to solar panels, to seals, to filters. It is composed of particles so fine that they behave almost like a fluid, working their way into every crevice and joint. And it is chemically toxic, full of perchlorates that, when inhaled or ingested in even small quantities, can cause severe thyroid damage and other long-term health problems. The Curiosity and Perseverance rovers had measured perchlorate concentrations in Martian soil at levels hundreds of times higher than what is considered safe on Earth. This was not a minor logistical issue. This was a question of whether humans could safely live in long-term contact with the Martian environment at all. Engineers tried to solve it. They proposed elaborate decontamination protocols, airlock systems designed to remove dust before colonists entered habitats, filtration systems that would scrub the air continuously. But every solution added mass, added complexity, added energy requirements, added points of potential failure. The dust problem alone was forcing Mars mission designs to grow heavier and more elaborate with each iteration. And the harder engineers worked on it, the more they realized that there might not be a fully satisfactory solution. The dust on Mars would be a chronic, never-ending hazard. Every EVA would risk contamination. Every piece of equipment would degrade faster than expected. Every colonist would be inhaling at least trace amounts of toxic material throughout their stay, no matter how carefully the systems were designed. The second crack was the water problem. Mars has water ice, yes, but extracting it had turned out to be far more difficult than early mission designs had assumed. The ice was buried beneath dry regolith in most accessible locations, requiring drilling and excavation equipment that was heavy, complex, and prone to failure in the cold and dust. The ice in many regions was mixed with perchlorates, which meant any water extracted had to be extensively purified before it could be used for drinking, agriculture, or even fuel production. And the regions of Mars with the most accessible water ice tended to be at higher latitudes, where temperatures were colder, sunlight was weaker, and landing was more dangerous. The places that were easiest to land on were poorest in water. The places that were richest in water were hardest to reach. This was a tension that no mission architecture had ever fully resolved. The third crack was the gravity question. For years, the assumption had been that Mars gravity, at 38% of Earth's, would be sufficient to prevent the most severe physiological effects of long-term low-gravity exposure. But as more data came in from astronauts who had spent extended periods on the International Space Station, and as researchers refined their understanding of how bone density and muscle mass and cardiovascular function respond to reduced gravity, the assumption began to look shakier. The truth was that no one knew whether 38% gravity was enough. There was no data on humans in partial gravity environments. Studies on the ISS could tell us what happened in microgravity. Studies on Earth could tell us what happened in full gravity. But Mars gravity was a gap in human experimental knowledge. It might be sufficient to maintain health. It might not. And if it was not, the implications were severe. Mars colonists might experience continued bone loss throughout their stays, regardless of exercise regimes. Children born on Mars might never develop the skeletal structure needed to function in Earth gravity. The colony might be biologically trapped, not just physically. While these doubts were accumulating about Mars, Titan was quietly accumulating advantages. The Cassini-Huygens mission, which had ended in 2017 with the controlled crash of the Cassini orbiter into Saturn, had left behind a treasure trove of data that researchers were still mining years later. Every paper that came out seemed to reveal something new and remarkable about Titan. The lakes were more extensive than anyone had realized. The subsurface ocean of liquid water, buried beneath the icy crust, appeared to be larger and more chemically complex than initial estimates had suggested. The atmospheric chemistry was producing organic compounds in quantities that staggered organic chemists, creating a natural laboratory of prebiotic chemistry that operated on a planetary scale. Titan was not just habitable in the narrow engineering sense. Titan was a chemically rich, dynamically active world with resources that Mars simply did not possess. The decisive moment, if there was one, came when researchers began running detailed comparisons of energy budgets for long-term settlements. On Mars, the energy economy was tight. Solar panels worked, but dust storms could reduce their output by 90% for weeks at a time. Nuclear power was an option, but launching nuclear material from Earth was politically and logistically difficult. Wind power was useless because the atmosphere was too thin to drive turbines effectively. Geothermal power required drilling deeper than any current mission had attempted. Every energy source on Mars came with significant caveats and limitations. On Titan, the energy picture was different in ways that mattered enormously. Solar power was much weaker because of the distance from the Sun, only about 1% of what's available on Earth's surface, which meant solar was essentially useless as a primary power source. But Titan had something Mars did not. It had wind. The thick atmosphere meant that even modest wind speeds carried real energy, enough to drive turbines effectively. It had a chemical fuel source sitting on its surface in the form of methane lakes. It had nuclear power options, since launching nuclear material to Titan posed no greater risk than launching it to Mars, and the longer mission duration justified the investment. And most remarkably, the temperature differential between the cold surface and any heated habitat was so extreme that it could be used to drive heat engines with very high efficiency. The cold itself, in other words, was a resource. The energy that flowed from a warm habitat to the frigid environment outside could be tapped and partially recovered. This was not possible on Mars. The temperature differential was too small. The arguments accumulated, slowly at first, then more rapidly. Papers began to appear in journals like Acta Astronautica and the Journal of the British Interplanetary Society, making the case that Titan, not Mars, was the realistic long-term destination for human settlement. Robert Zubrin, the founder of the Mars Society and one of the most prominent advocates for Mars colonization, found himself in increasingly heated debates with researchers who had once been his allies. The case for Titan was not refuted. It was simply uncomfortable, because if Titan was the better destination, then everything that had been built around the Mars First assumption had to be reconsidered. The mission timelines, the propulsion priorities, the international agreements, the funding streams, the dreams of an entire generation of engineers and scientists who had spent their careers planning for Mars. And there was one more crack, the deepest one, the one that no one wanted to acknowledge publicly. If Titan was the better destination, then the people who went would face a journey and a separation so profound that it would make Mars colonization look like a weekend trip. The closer destination might be the wrong one. The farther destination might be the right one, and humanity might have to choose between two terrible options: a flawed but reachable Mars or a better but functionally unreachable Titan. The decision, if it ever came, would not be easy. It would not be clean. It would tear the space community apart. To understand why Titan colonization is technically possible at all, we have to talk about how we would actually get there. Because everything we have discussed so far, the atmosphere, the pressure, the resources, the radiation shielding, becomes meaningless if we cannot physically deliver humans across nearly 1 billion miles of empty space. The journey to Titan is not a longer version of the journey to Mars. It is a fundamentally different category of mission, requiring technologies and engineering solutions that either do not yet exist in operational form or exist only as carefully studied designs on paper. And the technology that makes Titan colonization conceivable, the one breakthrough that turns a fantasy into a feasibility study, is propulsion. Chemical rockets, the workhorse propulsion technology that has carried every human mission into space, are simply not adequate for sending crews to Saturn. The math is unforgiving. A chemical rocket burning the most efficient propellants we know, liquid hydrogen and liquid oxygen, can achieve a specific impulse of around 450 seconds, which is the engineering term for how much thrust you get per unit of propellant burned. This is good enough to get to Mars, with a journey of 6 to 9 months. It is not good enough to get to Titan in any reasonable time frame. Using chemical propulsion alone, a Titan mission would require either a journey of 6 to 8 years one way, using a slow Hohmann transfer orbit that drifts outward through the solar system, or impossibly massive quantities of propellant to achieve faster trajectories. Either option fails. A crew cannot survive 8 years in transit without enormous habitat modules and life support systems that themselves require more propellant to launch. And the propellant required for faster trajectories exceeds anything we could realistically lift from Earth, even with the largest super-heavy launch vehicles currently in development. The solution that emerges, the one that planetary scientists and propulsion engineers keep returning to in their proposals, is nuclear. Specifically, nuclear thermal propulsion and nuclear electric propulsion, two related technologies that use the energy from nuclear reactors instead of chemical reactions to accelerate propellant. Nuclear thermal propulsion works by passing a propellant, usually liquid hydrogen, through a nuclear reactor that heats it to extremely high temperatures, then expelling it through a nozzle to produce thrust. The specific impulse of nuclear thermal propulsion is roughly 900 seconds, twice that of the best chemical rockets. This sounds like a modest improvement, but because the rocket equation is exponential, doubling the specific impulse dramatically reduces the propellant required for a given mission. A Titan mission using nuclear thermal propulsion could potentially be completed in 3 to 4 years one way, with propellant requirements that, while still enormous, are at least within the realm of feasibility. Nuclear electric propulsion takes a different approach. Instead of heating propellant directly, a nuclear reactor generates electricity, which is then used to power ion engines or plasma thrusters that accelerate small amounts of propellant to extremely high velocities. The specific impulse of nuclear electric propulsion can reach 5,000 to 10,000 seconds, an order of magnitude better than chemical rockets. The downside is that the thrust is very low, which means the spacecraft accelerates slowly over months or years rather than minutes. For a Titan mission, this might be acceptable. A nuclear electric spacecraft could accelerate continuously for a year, coast through the middle of the journey, then decelerate continuously for another year, arriving at Titan with much less propellant than any chemical mission would require. Both technologies have been studied for decades. Nuclear thermal propulsion was first developed in the United States during the 1960s under a program called NERVA, which stood for Nuclear Engine for Rocket Vehicle Application. Prototype engines were built and tested on the ground at facilities in Nevada. The engines worked. They produced the predicted thrust at the predicted specific impulse. They demonstrated that nuclear thermal propulsion was not theoretical but practical. The program was cancelled in the early 1970s, not because of technical failure, but because of changing political priorities and the end of the Apollo era. The hardware was mothballed, the expertise dispersed. The technology sat dormant for almost half a century. Only in recent years has there been renewed interest, with both NASA and the Department of Defense funding new programs to develop modern nuclear thermal engines for potential use in deep space missions. Nuclear electric propulsion has a similar history. Small-scale ion engines have been used on robotic spacecraft for years, with the Dawn mission demonstrating their reliability on a journey to the asteroid belt. But the power levels required for human missions are vastly larger. You need megawatts of electrical power, not the kilowatts that current ion engines use. This requires nuclear reactors specifically designed for space operation, lightweight, reliable, capable of operating continuously for years. NASA has developed concepts for such reactors, including the Kilopower program that demonstrated small fission reactors producing 10 kilowatts of electricity. Scaling up to the megawatt level required for human missions is a significant engineering challenge, but not an insurmountable one. The physics is well understood. The materials exist. The remaining work is engineering, testing, qualification, and the political will to actually build and launch nuclear systems. There is a third propulsion concept that is sometimes discussed for Titan missions, though it remains more speculative. Fusion propulsion, which would use controlled fusion reactions to produce extremely high specific impulse and reasonable thrust, would make Titan missions almost routine. Travel times could potentially be cut to a year or less. The energy density of fusion fuels far exceeds anything achievable with fission. But fusion propulsion requires controlled fusion reactors, and despite decades of research, we still do not have controlled fusion working reliably even in laboratory settings. It is a technology of the future, perhaps the relatively near future, but not yet something we can build and fly. For the foreseeable future, then, a Titan mission would rely on some combination of nuclear thermal and nuclear electric propulsion, possibly with chemical stages for the initial launch from Earth orbit. The spacecraft would be enormous by any current standard. We are talking about vehicles with masses in the thousands of tons, assembled in low Earth orbit from components launched on multiple heavy-lift missions. The habitat modules would be larger and more sophisticated than anything ever flown, because the crew would be living in them for years. The radiation shielding would need to be substantial, both for the journey itself and to protect against the radiation environment around Jupiter as the spacecraft used gravity assists to gain velocity. The life support systems would need to be more closed-loop than anything that has ever existed, recycling air and water with near-perfect efficiency over years of operation without resupply. And there is the question of communication. At Saturn's distance, radio signals take between 67 and 85 minutes to travel one way, depending on the relative positions of Earth and Saturn. Round-trip communication takes more than 2 hours, even in the best case. This is not just an inconvenience. This is a fundamental change in the relationship between the crew and Earth. There is no real-time conversation possible. There is no immediate technical support. If something goes wrong on the spacecraft or on Titan, the crew has to solve it themselves, because by the time they describe the problem to Earth and receive a response, hours have passed. They are alone in a way that no human crew has ever been alone before. The technology, then, exists in concept, if not yet in operational form. The propulsion systems that could carry humans to Titan have been studied, designed, and in some cases partially developed. The life support systems that could keep them alive for years have been demonstrated in pieces, though never assembled into a complete operational system. The habitats, the shielding, the navigation, the communications, all of it is engineering, not physics. None of it requires breakthroughs that violate known laws of nature. It all requires sustained investment, political commitment, and the willingness to build hardware that has never been built before. Whether humanity will actually make those investments is a different question, but the technical foundation, the ladder we would climb to reach Titan, is there. It is real. It is waiting to be built. The question is no longer whether Titan can be reached. The question is what we find when we arrive and what it costs us to stay. Imagine, for a moment, the first crew to actually arrive. Picture them descending through the orange haze, their spacecraft's heat shield glowing as it bleeds away velocity in Titan's thick atmosphere, parachutes deploying in a sky that no human eyes have ever seen up close. The descent takes hours, not minutes. Titan's atmosphere is so dense and the gravity so low, only 1/7 of Earth's, that parachutes are extraordinarily effective. The crew has time to watch the landscape resolve beneath them, time to see the orange light filtering through the haze, time to understand, slowly and irrevocably, that they have arrived somewhere genuinely new. And then they touch down, gently, on a surface that has waited 4.5 billion years for the soles of human boots. The first discovery, the one that hits them before anything else, is the sky. They had been briefed for years. They had studied the Cassini-Huygens data until they could recite it in their sleep. They knew intellectually what to expect. But knowing and seeing are not the same thing. The sky on Titan is not blue. It is not the pink of Mars or the black of the moon. It is orange. Deep, golden, smoky orange, like the light at the end of a long sunset, except that this light does not fade. It is the permanent color of day on Titan, produced by the photochemical haze that drifts in layers through the upper atmosphere, scattering sunlight in ways that make the entire dome of the sky glow with a warm, almost honey-colored radiance. The sun itself, when visible at all, appears as a small, faintly luminous disk, no brighter than a full moon on Earth. There are no shadows in the sharp, clean sense that humans are used to. Everything is softly lit, evenly illuminated, as if the world were perpetually wrapped in a thin fog of amber light. The first scientific reaction, transmitted back to Earth with its 80-minute delay, is one of stunned confirmation. Every measurement that had been made remotely turns out to be accurate. The atmospheric pressure reads at 1.5 atmospheres, exactly as predicted. The temperature reads at -290 degrees Fahrenheit, almost exactly what the models had forecast. The air composition is dominated by nitrogen, with the expected percentage of methane, the same chemistry that Cassini and Huygens had measured nearly half a century earlier. The crew is standing on a world that conforms, in every measurable respect, to what humanity had thought it would be. And yet the experience of standing there, of actually being present on the surface, reveals things that no instrument had been able to capture. The first thing that strikes them is the silence, not the silence of vacuum, which they had experienced during their transit and during their lunar training. The silence of a world where the atmosphere can carry sound, but where there is nothing to make sound except the wind. Titan has wind. Light wind, usually, drifting at a few miles per hour. But the air is so dense that even gentle wind produces a noticeable rustling, a soft whisper against their suits, a sound that has not been heard by human ears in any environment beyond Earth. They can hear themselves move. They can hear the crunch of icy gravel under their boots. They can hear, faintly, the distant patter of methane rain falling somewhere in the orange distance. This is the first world humans have ever set foot on where the environment makes sound on its own. The second thing that strikes them is how easy it is to move. Titan's gravity is about 14% of Earth's, much weaker than Mars and weaker even than the Moon. A person who weighs 180 pounds on Earth weighs only about 25 pounds on Titan. Walking feels effortless. Jumping is exhilarating. The crew quickly discovers that they can leap several meters off the ground with minimal effort, drifting back down through the dense atmosphere with the slow grace of a feather. Within hours, one of them tries something that no human has ever attempted before. They strap on a pair of small wings, prototype devices designed by engineers back on Earth specifically for this purpose. They flap. They lift off the ground. They fly. Not metaphorically, not assisted by jet packs, but actually fly, like birds, using the combination of low gravity and thick atmosphere to make human-powered flight possible for the first time in the history of the species. The video transmitted back to Earth shows a human being soaring briefly through an orange sky on a moon of Saturn. It is one of the most extraordinary images ever produced, and when it eventually reaches mission control nearly an hour and a half after it was recorded, the room erupts in tears. But the third discovery, the one that begins to unsettle the crew, is the cold. They had known about the cold. They had trained for it. Their suits were specifically designed to keep them warm in temperatures that would freeze nitrogen out of the air. But knowing about cold and feeling it work against your suit are different things. The cold on Titan is not the bracing chill of an Earth winter. It is a force, a presence, an active drain that pulls heat from every surface continuously. Their suits are warm enough to keep them alive, but they can feel the cold pressing in. They can see, when they look closely, the way frost forms on their faceplates almost immediately when they exhale through their suits' recyclers. They can sense the way the cold makes the dense atmosphere feel almost liquid, viscous, like wadding through invisible syrup. The cold is everywhere, all the time, and they begin to understand, in a way that no briefing could have prepared them for, that this world is not warm and welcoming. It is welcoming in its chemistry, in its pressure, in its shielding. But it is not warm. It will never be warm. And the moment any heating system fails, the cold will reclaim everything in minutes. Their first habitat is already on the surface, having been delivered by uncrewed missions years earlier. They walk to it slowly, savoring the strangeness of the landscape. The ground beneath their boots is a mixture of water ice, frozen as hard as granite at these temperatures, and darker organic deposits, the accumulated residue of billions of years of atmospheric chemistry settling out of the sky. The terrain is gently rolling, marked here and there by channels that were carved by ancient methane rivers, smoothed by erosion in ways that look almost familiar. Almost, but not quite. The pebbles are too round. The light is too even. The horizon is closer than it should be because Titan is smaller than Earth and the curve of the world is sharper. Every detail is slightly off, slightly wrong, slightly alien. They are walking through a landscape that the human visual system has not evolved to interpret, and the cumulative effect, over hours, is disorienting in ways that no one had warned them about. The habitat itself, when they reach it, is a low dome partially buried in the icy soil. It does not need to be reinforced against vacuum because there is no vacuum. The internal pressure can be set to match the external pressure, which means the walls do not have to bear the enormous load that Martian or lunar habitats must withstand. This is one of Titan's greatest gifts to its colonists. The habitat is a simple structure, almost embarrassingly conventional by space architecture standards, built from materials that would not look out of place on an Antarctic research station. The complexity is all on the inside, in the life support systems, the atmospheric processes, the heating systems that fight back against the eternal cold. But the structure itself is unremarkable. It is a house on a moon of Saturn, and the crew walks through its airlock and removes their suits and stands inside, breathing Earth air, looking out through the windows at an orange sky and a frozen world, and they realize that they are home now, whether they meant to be or not. The first major discovery, transmitted to Earth in the days following landing, is not anything they expected. It is something the orbiters had hinted at, but never confirmed. The methane rain, falling somewhere in the distance during their descent, has done something to the surface that no one had predicted, and the implications of that discovery, when fully understood, will reshape every plan that humanity had made for what life on Titan could become. The discovery begins with a routine sample collection. 3 days after landing, 2 members of the crew suit up and venture out to a nearby channel, one of the dry riverbeds visible from orbit, to collect material for analysis. They use specialized tools designed to scoop up the icy gravel without contaminating it with their own equipment's lubricants or thermal residue. They seal the samples in insulated containers and carry them back to the habitat's small laboratory, where they begin running the standard suite of tests: composition, mineralogy, organic chemistry, isotope ratios, everything by the book, exactly as their training had prepared them for. The results, when they come back, do not match anything in the book. The organic compounds detected in the sample are not the simple hydrocarbons that Cassini had measured in Titan's atmosphere. They are something more complex, long-chain molecules, polymerized structures, the kinds of compounds that, on Earth, are associated with biological processes or with extremely sophisticated industrial chemistry. The crew runs the tests again. They run them a 3rd time, using different instruments. The results hold. The samples contain organic molecules of a complexity that should not exist on a world this cold, with chemistry this slow, without some kind of process actively concentrating and assembling them. The lead astrobiologist on the crew, a woman who had spent 20 years preparing for this exact moment, calls an emergency meeting. She lays out what they have found. The molecules are not proof of life. She is careful to emphasize this. They are not cells, not anything that could be called alive in the conventional sense, but they are not what abiotic chemistry produces either. They are something in between, something that suggests that Titan's environment, despite the cold, despite the slowness of all chemical reactions at these temperatures, has been running prebiotic chemistry experiments for billions of years. The same kinds of experiments that, on Earth, eventually produced living cells. Titan, it appears, has been doing chemistry homework on a planetary scale for longer than Earth has existed, and the results are sitting on its surface, frozen into the channels and the dunes and the lakebed sediments. The transmission to Earth, when it arrives nearly an hour and a half later, triggers the kind of scientific reaction that happens perhaps 2 or 3 times in a generation. Astrobiology departments around the world erupt. Researchers who had spent careers arguing that Titan might be a chemical laboratory for understanding the origin of life suddenly find themselves vindicated in ways they had never expected. Researchers who had argued the opposite, that Titan was too cold for any meaningful prebiotic chemistry, scramble to revise their models. The implications ripple outward through every field that touches on the question of life beyond Earth. If Titan has been quietly performing prebiotic chemistry for 4 billion years, then the universe is far more chemically active than anyone had assumed. The conditions for life are not rare. They are everywhere. We just had not been looking in the right places. But the immediate question, the one that the crew has to grapple with in the hours after the discovery, is what this means for the colony. The plan had always been to establish a permanent human presence on Titan. To begin extracting resources, building infrastructure, expanding the habitat into something that could eventually support hundreds or thousands of people. But if Titan is a chemically active world with prebiotic molecules in its sediments, then every action the colonists take risks contaminating that chemistry. Every dropped tool, every spilled fuel, every breath of warm air vented from a habitat introduces compounds and conditions that could interfere with whatever Titan has been doing on its own for billions of years. The crew finds themselves in an ethical position that no previous space mission has ever faced in such acute form. They are settlers, but they are also potentially contaminators of one of the most scientifically valuable environments in the solar system. This is where the second discovery emerges. It comes from a different direction, from the team studying Titan's atmosphere using instruments on the habitat's roof. They had been measuring the composition of the air with high precision, looking for any seasonal variations or unexpected chemistry, and they had found something. The methane in Titan's atmosphere, the methane that had puzzled scientists for almost a century because it should have been destroyed by ultraviolet light long ago, was being replenished, not by geological processes, which had been the leading hypothesis for decades, but by something else. The isotope ratios were wrong for purely geological methane. There was a fraction of the atmospheric methane, small but measurable, that carried isotopic signatures consistent with biological production. Not definitive proof. The crew is careful, again, to emphasize that nothing they have found constitutes proof of life. But the methane signatures, combined with the complex organic molecules in the sediments, paint a picture that is increasingly difficult to explain without invoking some kind of active chemistry, either biological or borderline biological, operating somewhere beneath the surface. The crew begins to suspect that the answer lies in the subsurface ocean. Beneath Titan's icy crust, hundreds of kilometers down, lies a vast ocean of liquid water mixed with ammonia and other compounds. The Cassini mission had detected its presence through gravitational measurements and through subtle distortions in Titan's rotation. The ocean is real, larger than all of Earth's oceans combined, kept liquid by the heat of Titan's interior and by the antifreeze effect of dissolved ammonia. And if life exists anywhere on Titan, the ocean is the most likely place. The crew cannot reach it directly. Drilling through hundreds of kilometers of ice is beyond any current technology. But they can look for indirect signs. They can search for places where material from the deep ocean might have made its way to the surface, through cryovolcanoes or through cracks in the icy crust. And as they begin to map these features systematically, using the rovers that had been pre-deployed years earlier, they start to find evidence of such transport. Patches of surface chemistry that look fundamentally different from the surrounding terrain. Compounds that should not exist in Titan's surface environment, but that would make sense if they had been transporting up from a warmer, wetter environment far below. The third discovery, the one that begins to make the crew genuinely uncomfortable, emerges from these mapping surveys. There are patterns in the surface chemistry. Patterns that are too regular to be random, too localized to be the result of broad atmospheric processes, too persistent to be transient phenomena. The crew begins to realize with growing unease, like the kind of patterns that ecosystems leave on a planet's surface. Concentrations of certain compounds in specific terrain features. Gradients of chemistry that change with depth and location in ways that suggest active transport. Not the dramatic, obvious signatures of life that we would see on Earth, where forests and oceans and cities reshape the planet's surface. Something quieter. Something that has been operating slowly for billions of years, leaving behind subtle traces that only become visible when you look at them with the right instruments, in the right places, with the right questions in mind. The colony's purpose, as defined by the mission planners back on Earth, had been to establish a permanent human presence and to begin the long process of transforming Titan into a second home for humanity. But the discoveries of the first weeks complicate that purpose in ways that no one had fully anticipated. If Titan harbors life, even simple, chemically modest life, then the colony's presence is not just a settlement effort. It is also an intrusion into one of the most scientifically precious environments humanity has ever encountered. And the crew, sitting in their habitat under an orange sky, watching the data come in night after night, begins to understand that they are not just settlers. They are also the first witnesses to something far stranger and far more profound than anyone had prepared them for. They are the first humans to confront, in real time, the possibility that we are not alone in the solar system. And the implications of that, for everything that comes next, are about to become almost unbearable. The pattern that emerges over the following months is unlike anything the crew, or anyone on Earth following the data, had anticipated. It is not the discovery of life in the dramatic sense. There are no microbes seen under microscopes, no cells captured on slides, no clear biological structures that anyone could point to and say, "This is alive." The evidence is more diffuse than that, more cumulative, more frustrating in its refusal to resolve into certainty. It is the pattern itself, the accumulating weight of small anomalies, that begins to feel inescapable. The crew expands their sampling program. They send rovers out to a dozen different sites across the landscape, collecting material from dune fields, from lake margins, from cryovolcanic features, from the icy plains that stretch between major geological structures. Every sample comes back with the same general picture. Complex organic molecules in concentrations that should not exist purely from atmospheric chemistry. Isotopic signatures that hint at active processes rather than passive accumulation. Subtle gradients in composition that vary with depth and location in patterns suggestive of biological activity, though never definitively proving it. The frustration is exquisite. The data is consistent with life. It is also consistent with extraordinarily complex prebiotic chemistry that we do not fully understand. The crew cannot resolve the ambiguity from the surface. To do that, they would need to reach the subsurface ocean, and that capability does not exist. But within the ambiguity, a new pattern begins to emerge that catches everyone off guard. The complex organic molecules in the surface sediments are not uniformly distributed. They are concentrated in specific places, in specific terrain types, in ways that suggest something is selecting for those locations. The areas near the methane lakes show different chemistry than the areas in the dune fields. The areas near cryovolcanic features show yet another signature. And when the crew maps these distributions carefully, comparing them to the orbital data accumulated over decades, they realize they are looking at something that resembles a global chemical ecology. Different regions of Titan are running different chemical experiments. The whole moon is, in a sense, a vast natural laboratory in which different conditions produce different outcomes, and the outcomes vary in ways that are too systematic to be random. This realization changes how the crew thinks about their settlement. They had assumed, like everyone before them, that Titan was a relatively uniform environment. Cold, hydrocarbon-rich, chemically interesting, but fundamentally homogeneous. The data was now telling them something different. Titan was a world of regions, of biomes in the loose sense of that word, of distinct chemical neighborhoods that interacted with each other in ways no one had previously appreciated. And the implications for colonization were enormous. Where you placed a settlement mattered, not just for engineering reasons, but for scientific and possibly ethical ones. Some regions of Titan were, apparently, more chemically active than others. Settling in those regions meant disturbing whatever chemistry was occurring there. Settling away from them meant living in less chemically interesting areas, but preserving the active ones for study. The crew begins to argue, gently at first, then more intensely, about what their long-term strategy should be. The mission plan had called for expansion, build out the habitat, bring more colonists from Earth, develop industrial capacity, begin extracting resources. But the discoveries of the first months were making the original plans seem reckless. To expand a settlement on Titan without first understanding what was happening chemically beneath their feet was to risk contaminating or destroying something irreplaceable. And yet the colonists could not simply do nothing. They needed to build infrastructure to survive. They needed to extract methane for fuel. They needed to expand their habitat as more crew arrived on subsequent missions. The tension between settlement and preservation was building, and there was no clear way to resolve it. The third major discovery, the one that pushes the situation from tense to almost intolerable, comes from a deep ice-penetrating radar survey conducted by one of the orbiters that had been deployed during the pre-colonization phase. The radar had been mapping the structure of Titan's icy crust, looking for places where the ice was thinner or where there might be liquid water reservoirs closer to the surface than the deep ocean. The data, when analyzed in detail, reveals something extraordinary. There are pockets of liquid water trapped within the ice, hundreds of meters to a few kilometers below the surface, in specific geological formations. These pockets are not connected to the deep ocean. They are isolated reservoirs, sealed within the ice for what may be hundreds of millions of years, and they are warm enough, due to local heat sources within the crust, to remain liquid despite the deep cold of Titan's surface environment. The implications are staggering. If life exists anywhere on Titan, these isolated subsurface reservoirs might be where it is easiest to find. They are accessible, in principle, by drilling. They are warm enough for liquid water chemistry. They have been isolated long enough that any life within them might have evolved in unique directions. And they are, the radar data suggests, more common across Titan than anyone had expected. There might be dozens of such reservoirs scattered across the moon, each one a potential laboratory of biology, each one a potential window into chemistry that has been running undisturbed since long before the dinosaurs walked on Earth. The crew begins to plan a drilling operation. It will take months to prepare. The equipment had been included in the pre-deployed cargo with exactly this possibility in mind, though no one had truly expected to use it so soon. The plan is to drill into one of the smaller, shallower reservoirs first, sampling the liquid water carefully to avoid contamination from the drilling fluids and from the surface environment. If they find evidence of life, even microbial life, it will be one of the most significant discoveries in the history of human civilization. If they find no evidence of life, the question of Titan's biological potential will not be resolved, but the constraints on it will tighten considerably. But before the drilling can begin, the crew makes another discovery, almost by accident. While conducting routine geological surveys near the habitat, one of the rovers encounters a small surface feature that catches the attention of the geologist on the team. It is a patch of terrain, perhaps 50 meters across, where the surface chemistry is dramatically different from the surrounding area. The methane and ethane concentrations are reduced. The complex organic molecules are present at higher concentrations than anywhere else they have measured. And there are faint, persistent emissions of gas from cracks in the surface, gas that contains chemical signatures suggestive of biological metabolism. The rover spends 3 days analyzing the site in detail. The conclusion, when it is finally transmitted to Earth, is cautious but unmistakable. This site, this small patch of seemingly ordinary Titanian terrain, is doing something that no purely abiotic process can easily explain. It is consuming methane. It is producing complex organics. It is, in a slow and modest way, behaving like a living ecosystem. The transmission, when it reaches Earth more than an hour after being sent, triggers what can only be described as a planetary moment. Scientific journals delay publication of other papers to accommodate the news. Governments call emergency meetings. Religious leaders issue statements. Television networks interrupt regular programming for hours. The discovery is not yet confirmed as life, technically. The crew, true to their training, refuses to use that word definitively. But the entire human species understands, in some collective way, that something has changed. We are not alone in the solar system. Or if we are, the line between life and non-life is far blurrier than we had ever imagined, and that itself is a discovery of equal magnitude. For the crew on Titan, the discovery transforms everything. They are no longer just colonists. They are no longer just scientists. They are the first witnesses to a second genesis, the first humans to encounter another origin of complex chemistry in the universe, and they are now responsible, in a way that nothing in their training had prepared them for protecting it. The discovery should have been a triumph. It should have been the moment that justified every dollar spent, every life risked, every year of separation endured. It was the moment humanity had been working toward since Aristotle first asked whether other worlds were inhabited. And in the immediate aftermath, in the first weeks after the announcement, it was celebrated as such. But as the dust settled, as the first wave of euphoria faded, the crew began to confront something they had not been prepared for. The discovery did not just change what Titan was. It changed what the colony could be. And it did so in ways that began to feel less like a gift and more like a paradox they could not solve. The first problem was contamination. The colony had been operating for months. The crew had walked across the surface, driven rovers across vast distances, extracted samples, vented warm gas from their habitat, sprayed lubricants on equipment, deposited trace amounts of human-associated chemistry across every site they had visited. None of this had seemed problematic when Titan was assumed to be sterile, or at most a chemical laboratory running purely abiotic experiments. But if Titan harbored life, even the slow, modest, methane-consuming life that the surface anomaly suggested, then every human action carried the risk of disturbing or contaminating that life in ways no one could fully assess. The crew had not just discovered something extraordinary. They had been walking through it for months, possibly destroying it without realizing they were doing so. The ethical implications cascaded outward. Some members of the crew argued for immediate restriction of all surface activities outside the habitat. No more sampling, no more rover expeditions, no more EVAs except for absolute emergencies. The colony should hunker down, they argued, while scientists on Earth and on Titan worked out a protocol for engaging with a potentially inhabited world. Others argued the opposite, that the discovery made expanded study more urgent, not less. If Titan harbored life, they needed to understand it before more colonists arrived, before industrial activities began, before the inevitable accidents and spills that came with any settlement effort. The debate was civil, professional, conducted in the careful language of scientists who had trained together for years. But beneath the surface, it was tearing the crew apart. The second problem was political. On Earth, the discovery had become the most significant news story in living memory, and the political response was immediate and chaotic. Governments that had funded the mission demanded updates faster than the communication delay allowed. Religious organizations issued statements ranging from celebration to condemnation. International bodies began drafting emergency treaties about the legal status of extraterrestrial life. Activists demanded the immediate withdrawal of the colony, arguing that humanity had no right to settle a world that was already inhabited. Industrial interests, conversely, argued that the discovery made Titan more valuable, not less, and pushed for accelerated development. The colony, which had been operating with a fair degree of autonomy due to the communication delay, suddenly found itself the focal point of competing political demands from across the entire human species. The crew tried to maintain their scientific focus. They continued their work. They published their findings. They cooperated with the scientific bodies on Earth that were trying to make sense of what they had found. But the political pressure was relentless, and the long communication delay made it almost impossible to respond effectively. By the time the crew received a request, formulated their response, and transmitted it back, the political situation on Earth had often shifted entirely. They were always responding to a past that no longer existed, addressing concerns that had already been replaced by new ones, satisfying demands that had already been retracted by the time their answers arrived. The communication delay, which had been a manageable inconvenience during normal operations, became a kind of slow torture during this period of intense political attention. The third problem was internal to the crew. The mission profile had assumed that the colonists would, over time, settle into the routines of long-term habitation. They would build infrastructure, conduct research, expand their capabilities, and gradually transform from a small expeditionary team into the nucleus of a permanent settlement. The discovery disrupted that trajectory in ways that affected every individual differently. Some crew members became increasingly absorbed in the scientific implications, spending nearly every waking hour analyzing data and writing papers. Others became withdrawn, struggling with the philosophical and ethical weight of what they had encountered. A few began to express doubts, quietly at first, about whether they should have come at all. The discovery had made their mission infinitely more meaningful. It had also made it infinitely more burdensome. The fourth discovery, which compounded everything, came from the drilling operation that had been planned before the surface anomaly was found. The crew had pressed forward with the drilling despite the political and ethical complexities, reasoning that they needed direct information about subsurface conditions to make any informed decisions about how to proceed. The drilling reached a small, isolated reservoir at a depth of about 2 kilometers, sampling liquid water that had been sealed within the ice for an estimated 300 million years. The samples were analyzed with extreme care, using protocols designed to detect even the faintest signs of biological activity. What they found surprised even the most optimistic researchers on the team. The reservoir contained living cells, not many. Concentrations were extraordinarily low, perhaps a few hundred cells per liter of water, but they were unmistakably biological. They had membranes, they had internal structures, they had metabolic activity that the instruments could measure in real time. They were not based on the same biochemistry as Earth life. They used different solvents, different molecular machinery, different energy gradients. But they were alive by any reasonable definition of the word, and they had been living in that isolated reservoir for hundreds of millions of years, evolving in complete isolation from any other ecosystem in the solar system. The transmission of this discovery to Earth caused something close to a collective shutdown of normal civilization for several days. The news consumed every channel of communication. The implications were too vast to process quickly. Life on Titan was not just possible, it was confirmed. It was different from Earth life in fundamental ways, which meant it had originated independently, which meant that the universe had produced life at least twice in the same solar system. The argument that life was common in the universe, which had been speculative for centuries, was now demonstrably true. We had found a second example, and it was sitting in a small sealed chamber beneath the icy crust of a moon of Saturn. For the crew, the discovery was simultaneously the greatest scientific achievement of their lives, and the moment when their colony became fundamentally untenable in its original form. They could not continue settling Titan in the way that had been planned. The presence of life, confirmed, isolated, and possibly unique in the universe, transformed Titan from a destination into a sanctuary. The question was no longer how to build a permanent human presence on Titan. The question was whether humans should be on Titan at all, and if so, how to be there without destroying what made Titan precious. The crew began drafting a new mission proposal, transmitted to Earth with the recommendation that all future colonization plans be suspended pending a thorough reassessment. The existing crew would remain, because returning was not realistic given the propulsion requirements and the years already invested. But the expansion plans, the additional crews being prepared for launch, the industrial development that had been envisioned, all of it needed to be reconsidered. The colony, as originally conceived, had become impossible. What it would become instead was a question that no one on Earth or on Titan was prepared to answer. And then, while the debate over Titan's future raged across two worlds, separated by an 80-minute communication delay, something happened in the colony that no one had anticipated. Something that would force the most painful reckoning yet. It happened during what should have been an ordinary maintenance cycle. One of the crew members, a structural engineer in her late 30s named in the public record only by her mission designation, had volunteered to conduct an external inspection of the habitat's primary heating exchanger. The unit had been showing minor performance fluctuations for several weeks. Nothing alarming, but enough to warrant a direct look. She suited up. She went through the standard pre-EVA checks. She exited the airlock into the orange twilight of a Titanian afternoon. And approximately 40 minutes later, while working alone on the exterior of the habitat at a position partially obscured from the other crew members, she stopped responding to communications. The crew's emergency protocols engaged immediately. 2 members suited up in record time. They found her within minutes. She was conscious. She was breathing. But she was sitting on the icy ground beside the heat exchanger, her tools laid carefully beside her, looking up at the sky. When they reached her, she turned her head slowly inside her helmet and told them in a calm voice that she did not want to go back inside. Not yet. She wanted to stay out here for a while longer. She wanted to look at the sky. They brought her in. They had to. Her suit's power reserves would not have lasted much longer in the cold. Inside the habitat, the mission medical officer ran every test in the protocol. Vital signs normal. Blood chemistry normal. Cognitive function tests within expected ranges. There was no medical explanation for what had happened. She was not hyposick. She was not hypothermic. She was not experiencing any acute psychiatric episode that the diagnostic tools could detect. She was simply, by her own quiet account, tired. Not physically tired. Tired in a way she could not fully articulate, a kind of weariness that had been building for months and had finally, on the surface that afternoon, surfaced in a form she could no longer suppress. The crew met that evening to discuss what had happened. The conversation was careful, kind, full of the language that professionals use when they are trying to address something that has no clean diagnostic category. But underneath the careful language was a recognition that something had shifted, not just for the engineer, but for all of them. The discovery of life on Titan had changed the meaning of their presence here. They were no longer pioneers in the simple sense. They were no longer settlers building toward a future. They were guests of a sort, in a place that had been doing its own slow chemistry for billions of years before humans existed, and would continue doing it for billions of years after humans were gone. The weight of that recognition, distributed unevenly across the crew, was beginning to express itself in different ways in different people. The mid-mission revelation, the one that reframes everything that came before, is not the discovery of life itself. It is what the discovery does to the colonists, because the original argument for colonizing Titan, the argument that had carried the day in the long debates back on Earth, had rested on a particular framing of what the moon was. Titan was a destination. Titan was a place humans could make their own. Titan was, in the language of mission planners, the most habitable world beyond Earth, which implicitly meant the most habitable for us. The chemistry was an interesting backdrop. The strange landscape was an aesthetic detail. The point of going was to be there, to build, to expand, to begin the long work of making humanity a multi-planet species. The discovery of life undoes that framing entirely. Titan is not a backdrop. It is a participant. It is a world with its own ongoing story, its own slow and patient work, its own claim on the future that does not need humans to validate it. The colonists arrived expecting to write the first chapter of a human history on Titan. They have instead arrived in the middle of a much older story, one that has been unfolding for longer than the existence of vertebrates on Earth, and they have to decide what role they are willing to play in it. Are they witnesses? Are they intruders? Are they partners in some collaboration that no one fully understands? The original mission concept does not contain language for any of these possibilities. The crew has to invent that language themselves, in real time, while the political pressure from Earth builds and the communication delay makes coherent dialogue almost impossible. What the engineer experienced on the surface that afternoon, the strange, exhausted moment of refusing to come inside, was not a breakdown in the clinical sense. It was, the crew came to understand over the following days, a kind of recognition. She had been looking at the orange sky, at the dim disk of the sun filtering through the haze, at the dark deposits on the icy ground that they now knew represented the work of a biosphere different from any Earth had ever produced. And she had understood, in a way that bypassed language. that she was no longer the protagonist of the story she was inside of. The colony was not the point of Titan. The colony was a small, recent, possibly temporary feature of a world that had been doing its work for ages and would continue doing it whether the colony succeeded or failed. The realization had not been distressing in the usual sense. It had been clarifying in the way that some hard truths are, and she had needed to sit with it for a while before she could come back inside and resume the role she had agreed to play. The crew, after talking through what had happened, found that several of them had experienced similar moments in the previous weeks, not as acute, not requiring intervention, but the same underlying recognition, surfacing in different ways. The astrobiologist had cried, alone in her quarters, after the first analysis of the deep reservoir samples confirmed living cells. The geologist had stopped taking samples for 3 days after one particular site survey, telling no one why, and had only resumed when he felt he understood what he was doing again. The mission commander had stopped reading the political traffic from Earth, delegating it to a junior officer, because the gap between what Earth was demanding and what the colony was experiencing had become too painful to bridge daily. They had all been processing something they had not been trained to process, and the engineer's moment on the surface had been the catalyst that brought it into the open. The mid-mission revelation, then, is twofold. The first part is the confirmation of life, which transforms the scientific and political landscape of the mission. The second part, the deeper part, is the realization within the crew that the meaning of their presence on Titan is not what they had been told it would be. They were sent as colonists. They have become something else, something for which no precedent exists in human history. They are the first humans to confront, in real time and in the place where it matters, the question of how to coexist with a form of life that originated independently of Earth. They cannot solve this question through engineering. They cannot solve it through political negotiation. They cannot solve it by following the mission plan, because the mission plan was written for a world that turned out not to exist. What they decide, in the weeks following the engineer's moment on the surface, is to do something that no space mission has ever done before. They draft a formal recommendation to Earth, signed by all members of the crew, requesting that Titan be designated a protected world under whatever international legal framework can be established quickly enough. They request that no additional colonization missions be launched. They request that their own colony be reclassified as a long-term research station rather than a settlement. They acknowledge that they themselves cannot return, that they will live out their lives on Titan, but they ask that no one else be sent to join them. They ask, in effect, for their own colony to be the last one. For the project of human colonization of Titan to end with them, so that whatever Titan is, and whatever it might become, can be preserved. The transmission of this recommendation to Earth, when it finally arrives more than an hour after being sent, will mark the beginning of the most painful debate in the history of human space exploration. It will divide nations. It will fracture institutions. It will force humanity to ask questions about what we owe to other forms of life, about what the purpose of expanding into space actually is, about whether the dream of becoming a multi-planet species was ever compatible with the reality of what we might find when we got there. And the crew, sitting in their habitat under an orange sky, will wait through the long communication delays for an answer that no one on Earth is prepared to give. The recommendation from the colony arrived at the Jet Propulsion Laboratory at 3 in the morning local time, on a Tuesday in spring. The duty officer who received the transmission read it 3 times before calling her supervisor. The supervisor read it twice and called the mission director. The mission director did not bother to read it before calling the agency administrator. By dawn, copies of the document were on the desks of cabinet officials in a dozen countries. By midday, it had been leaked to the press, and by evening, the recommendation from the 7 colonists on Titan had become the most discussed document in human civilization. What it triggered was not just political controversy. It was a complete and forced reassessment of nearly every assumption that had guided humanity's relationship with the cosmos for the previous century. The first thing that broke was the framework of planetary protection. The international agreements that have governed space exploration since the 1960s, primarily the Outer Space Treaty and its subsequent protocols, had been written with certain assumptions in mind. They assumed that contamination concerns ran primarily in one direction, that Earth life might contaminate other worlds. They assumed that any extraterrestrial life that might be encountered would be microbial, simple, and easily quarantined. They assumed that human exploration and eventual settlement of other worlds was a goal worth pursuing, and that scientific and ethical concerns could be balanced against that goal through reasonable regulatory frameworks. None of these assumptions survived the transmission from Titan. The colony was already there. Contamination had already occurred. The life that had been found was not microbial in the simple sense, but a complex biosphere that had been operating in isolation for hundreds of millions of years. And the colonists themselves, the people the framework had been designed to support, were now asking for the framework to be reversed. Scientific institutions were forced to confront questions they had been deferring for decades. The standard model of how life originates, built around the assumption that Earth was the only known example, had to be expanded to accommodate a second independent origin in the same solar system. This sounded like a minor technical adjustment, but its implications cascaded through every field that touched on the origin and distribution of life. If Titan had produced life independently, then the conditions for life were far more permissive than anyone had assumed. The galaxy was likely full of biospheres, most of them probably unreachable, all of them probably different from Earth in ways we could not easily anticipate. The Drake equation, that famous attempt to estimate the number of communicating civilizations in the galaxy, had always been heavily uncertain. After Titan, even its less ambitious cousin, the simple question of how many planets and moons hosted any form of life, became impossible to estimate with the old assumptions. The numbers, whatever they were almost certainly far larger than scientists had been comfortable predicting. The astrobiology community, which had spent decades on the margins of mainstream science, suddenly found itself at the center of a global conversation. Researchers who had been arguing for years that life might exist in unusual places, in the subsurface oceans of Europa or Enceladus or Titan, in the cloud layers of Venus, in the deep ice of Mars, found their arguments vindicated in the most dramatic possible way. But the vindication came with a heavy responsibility. If Titan had life, then Europa probably did too. Enceladus probably did. Several other locations in the solar system became candidates not just for scientific exploration, but for the same kind of ethical reassessment that the Titan colony was forcing. The pattern of human expansion into space, which had assumed an empty solar system waiting for us to fill it, suddenly looked very different. We were not the only residents of the system. We might not even be the most numerous, depending on how you counted. The economic implications were equally disruptive. The space industry had been built, increasingly over the previous decades, around the assumption that the resources of the solar system were available for human use. Asteroid mining ventures had attracted billions in investment. Plans for extracting water from the Moon, helium-3 from lunar regolith, hydrocarbons from Titan, and various minerals from Mars had been the basis of long-term business plans across multiple companies and nations. The discovery of life on Titan threw all of these plans into question. If Titan was off-limits, what about Europa? What about Enceladus? What about any body in the solar system that might harbor life we had not yet found? The default assumption that worlds without confirmed life were available for development had to be inverted. The new default, at least until thorough surveys had been conducted, might have to be that worlds without confirmed sterility were protected. Industries that had been planning for expansion suddenly faced the possibility of permanent restriction across most of the solar system. The political response varied dramatically by country and by ideological orientation. Some governments embraced the colonists' recommendation immediately, seeing in it an opportunity to position themselves as leaders in a new era of ethical space exploration. Others resisted it strongly, arguing that the colonists had exceeded their mandate, that the discovery did not justify the recommendation, that humanity could not afford to abandon its expansion into space because of what amounted to a single biosphere on a single moon. The debate was fierce and often bitter. Diplomatic relations between countries that took different positions deteriorated. Internal politics within countries fragmented along new lines, with traditional alliances breaking down as the Titan question cut across familiar political categories. Religious leaders entered the debate from every conceivable angle, some arguing that the discovery of independent life was a theological revelation that demanded humility and restraint, others arguing that it was a confirmation of humanity's special role as stewards of the cosmos and required active engagement rather than withdrawal. The colonists themselves became, against their will, the most famous human beings alive. Their faces, their voices, their slow, careful transmissions from across the gulf of the solar system were broadcast constantly. They had not asked for this. They had asked for the opposite, for the quiet authority to let Titan continue its work without further human interference. But the communication delay made it impossible for them to manage their own public profile. By the time they could respond to any portrayal of themselves, the portrayal had been repeated, amplified, distorted, and replaced by another one. They became symbols of competing causes that they had not chosen. Environmentalist movements claimed them as champions of cosmic conservation. Expansionist movements denounced them as traitors to humanity's future. Religious movements claimed them as prophets of various theological positions. The colonists, who had simply been trying to do the right thing in an impossible situation, watched all of this unfold across the lag of light minutes and could do almost nothing to influence it. What changes, in the broadest sense, is humanity's understanding of its own place in the universe. For most of recorded history, humans had assumed that we were, in some sense, the center of the cosmic story. Even after Copernicus moved Earth from the literal center of the universe, the assumption persisted that humans were the protagonists of whatever drama the universe was unfolding. We were the species that had developed language, technology, civilization. We were the species that had begun to explore beyond our planet. We were the species that, by any measure that mattered to us, was the most significant feature of the known universe. The discovery of life on Titan does not refute this assumption directly. The life that has been found is not technological. It has not built civilizations. It has not, as far as we can tell, asked questions about its own existence. But its presence shifts something nonetheless. We are not alone in the production of life. We are not unique even in our own solar system. The universe produces life, in different forms, in different chemistries, in different places. We are one expression among many. We are still significant, but our significance is no longer unchallenged. And the question of what we do with that recognition is the question that the next phase of human history will have to answer. The Titan colony, in the months and years following their recommendation, becomes the test case for that answer. Whatever humanity decides about Titan will set the precedent for everything that comes after. And the cost of getting that decision wrong in either direction may be greater than anything we have ever faced as a species. The question that emerges from all of this, the question that every thoughtful person on Earth has to confront in the years following the colony's recommendation, is what this means for us, not for humanity in the abstract, not for the species as a statistical entity. For us, the individuals living our lives on Earth, who will never go to Titan, who will never make decisions about its future, who will simply live in the world that the Titan question is reshaping around us. And the answer, when it begins to clarify in the months and years that follow, is more profound and more personal than most people had expected. The first change is in the way we look at the sky. For most of human history, the night sky had been a kind of decorative background, a beautiful but distant phenomenon that featured in poetry and religion, but not in the daily lives of most people. The space age had changed that gradually, making the planets and moons familiar in a way they had not been before. But familiarity is not the same as kinship. Mars had been familiar for decades, but it was a desert. The moon had been familiar for centuries, but it was a rock. The other worlds we knew about were places in the abstract sense, but they were not inhabited. They were not, in any meaningful sense, neighbors. After Titan, this shifts. Saturn becomes, almost overnight, a different kind of object in the sky. It is no longer just a beautiful planet with rings. It is the home, or near the home, of the only other biosphere we know about. The orange dot in the haze around Saturn, the dot too faint to see with the naked eye but easily resolved by even modest telescopes, becomes a place where life is happening right now, has been happening for hundreds of millions of years, will continue happening long after we are gone. Looking up at Saturn becomes a different experience than it was before. The universe is no longer empty in the way it had seemed. The second change is in how we think about ourselves. For thousands of years, the philosophical and religious traditions of human civilization had grappled with the question of what we are and why we exist. Many of these traditions had assumed, sometimes explicitly and sometimes implicitly, that the answer involved our uniqueness. We were the rational animal, the species made in the image of the divine, the creature chosen for a special purpose. Even secular humanism, in its various forms, had often rested on the assumption that human consciousness was a singular and precious phenomenon, perhaps the only one of its kind. The discovery of life on Titan does not contradict any of these traditions directly. The life on Titan is not conscious in any way we can detect. It is not rational in any sense that we recognize, but the discovery shifts the frame in which the traditions operate. We are no longer the only biosphere in the solar system. We are not, even within our own immediate cosmic neighborhood, alone in producing the phenomenon of life. The traditions that depended on a particular kind of uniqueness have to be reconsidered. Some of them adapt easily, others struggle. All of them are changed in ways that ripple through every culture on Earth. The third change, and perhaps the most personal, is in how we think about the future. For decades, the dream of human expansion into space had been a kind of secular hope for many people, a reassurance that the species had a future beyond the constraints of a single planet. Mars colonies, lunar bases, asteroid mining. Eventually, in some distant future, voyages to other stars. This dream had served different purposes for different people. For some it was a literal goal, something they wanted to participate in or witness. For others it was a metaphor, a way of believing that humanity's story would continue even if any particular individuals did not. The Titan discovery complicates this dream in ways that take time to absorb. If most of the worlds we might colonize turn out to have their own biospheres, then the dream of expansion has to be reconciled with the responsibility of preservation. We cannot simply spread across the solar system. We have to choose, carefully and slowly, where it is appropriate for us to be and where it is not. The dream of becoming a multi-planet species does not die, but it transforms into something more constrained, more ethical, more humble than the original vision. We may still expand, but not as conquerors. We may still settle other worlds, but only those that turn out to be genuinely empty, and the burden of proof for emptiness becomes much higher than it had been before. What this means for the average person, for the individual living their life on Earth, is harder to articulate. The Titan discovery does not directly change the price of bread or the prospects of finding a job or the quality of medical care. It does not solve any of the immediate problems that occupy most people's daily attention, but it sits in the background of everything, a presence that subtly reshapes how people think about their own lives. The recognition that life is not a one-time accident on a unique planet, but a recurring phenomenon that the universe produces under appropriate conditions, changes the meaning of being alive. We are not the lonely outpost of awareness in a vast and empty cosmos. We are one expression of something the universe does. The phenomenon of life, of which we are a part, is bigger than us, older than us, more varied than we had imagined. This is, depending on temperament, either reassuring or terrifying or both, but it is impossible to absorb without being changed by it. The Titan colonists, in their isolated habitat under an orange sky, become a kind of symbol for this change, though not in the way that their original mission had imagined. They had been sent as pioneers in the old sense, the first humans to extend our reach beyond the inner solar system and establish a permanent foothold among the outer worlds. They became, instead, witnesses to something that nobody on Earth had been prepared for, and their decision to ask that no more colonists be sent became a kind of statement about what humanity might choose to be in this new era. They were not refusing humanity's future. They were, in their own careful way, redefining what that future could mean. The version of expansion that involved spreading across the solar system without regard for what was already there was, by their own assessment, no longer viable. What replaced it would have to be invented by future generations in conversations that the colonists themselves would not live to see resolved. For the colonists personally, the implications were both elevating and crushing. They were, in some sense, the most important human beings alive, the people whose decisions and discoveries would shape the next era of human history. They were also, in another sense, prisoners. Their bodies had adapted to Titan's low gravity over the months and years of their stay, in ways that probably made return to Earth impossible, even if return had been technically feasible. The cumulative radiation exposure from their journey, their stay, and the cosmic rays that penetrated even Titan's thick atmosphere had built up to levels that would significantly shorten their lives compared to their counterparts on Earth. The psychological weight of what they had encountered, the daily reality of living in a place that they now understood was inhabited by another form of life, was not something any of them had been trained to bear. They became, in a sense, the saints and martyrs of a new cosmic religion that had not yet developed its language. They were honored. They were burdened. They were both, simultaneously and inextricably. What this means for humanity, in the longest possible view, is that we have crossed a threshold from which there is no returning. We have confirmed that we are not alone. We have learned that the universe produces life in places and in forms that we had not anticipated. We have, through the actions of 7 people on a distant moon, begun the long process of figuring out what kind of cosmic citizens we want to be. The Titan colony is not just a settlement. It is a hinge point in the history of our species, the place where we began to learn what it actually means to share the universe with others. What remains unanswered, after everything the colonists have discovered and everything humanity has been forced to grapple with, is staggering. The questions outnumber the answers by a wide margin, and many of the most important questions are ones that cannot be addressed with current technology or current resources, possibly for generations. The colonists themselves know this. They write about it in their transmissions back to Earth, in the careful scientific language of researchers who understand that they have opened a door but have not stepped through it. They have confirmed that life exists on Titan. They have not, in any meaningful sense, understood it. And the work of understanding it, if humanity chooses to undertake that work at all, will require missions and capabilities that no one has yet built. The first unanswered question is the origin of Titan's life. The cells found in the isolated subsurface reservoir are unmistakably biological, but their biochemistry is different from Earth's in fundamental ways. They use different molecules to store information, different mechanisms to generate energy, different membrane structures to separate themselves from their environment. This raises a profound puzzle. Did Titan's life originate on Titan, or did it arrive from somewhere else? The independent origin hypothesis is the most exciting, because it would confirm that life arises spontaneously under appropriate conditions, and that the universe is full of biospheres. But the alternative, that life on Titan and life on Earth share a common ancestor, possibly carried between worlds on debris from ancient impacts, cannot be ruled out without much deeper analysis. If there is a connection between the 2 biospheres, however ancient and tenuous, then the distinction between us and them is not as clear as it first appeared. We might be cousins, in some sense that biology has not yet developed the language to express. Resolving this question would require sampling the deep subsurface ocean, sequencing the genetic material of multiple organisms, and comparing them in detail to Earth life. The technology to do any of this on Titan does not yet exist. The second unanswered question is the extent and diversity of Titan's biosphere. The colonists have found life in one isolated reservoir. They have found chemical evidence consistent with life in other places, including the surface anomaly that consumed methane and produced complex organics. But they have not been able to confirm life across the wider moon. The deep subsurface ocean, which the colonists believe is the likely source of most of Titan's biological activity, remains entirely inaccessible. Drilling through hundreds of kilometers of ice to reach it is beyond any current capability and may remain so for decades or centuries. The surface biosphere, if such a thing exists, is probably sparse and slow, operating at temperatures so cold that any metabolic activity proceeds at speeds millions of times slower than on Earth. Mapping it would require missions of unprecedented sensitivity, capable of detecting biological signatures across vast areas without disturbing them. The colonists can do some of this work, but they are limited by their equipment and by the ethical constraints they have placed on themselves. The full picture of Titan's biosphere may not emerge for generations. The third unanswered question is what the discovery means for the search for life elsewhere. If Titan harbors an independent biosphere, then Europa probably does too. Enceladus, with its plumes of water vapor erupting from a subsurface ocean, becomes an obvious next target. The ice moons of Uranus and Neptune, largely unexplored, suddenly become destinations of major scientific interest. The cloud layers of Venus, where some researchers have suggested microbial life might exist in droplets of sulfuric acid, demand renewed investigation. Even Mars, which had been considered probably sterile based on decades of robotic exploration, has to be re-examined with new eyes. The discovery of life on Titan does not directly tell us whether life exists in any of these other places, but it shifts the prior probability dramatically. Life in the solar system is no longer a question of whether, but a question of where and how much. The fourth unanswered question is the most uncomfortable. What do we do about the colony itself? The colonists are there. They cannot return. They have asked that no more humans be sent to join them. But they themselves remain on Titan, living their lives, conducting their research, slowly agging in the orange twilight of a world that is not theirs. They will die there. Their bodies will remain on Titan, frozen and preserved after they are gone. Their habitat will eventually fail, their equipment will eventually break down, their presence will eventually fade. What happens then? Does humanity send a mission to recover their remains and their records? Does the colony become a memorial, preserved as a kind of monument to the first humans to encounter another biosphere? Does it simply decay, slowly absorbed back into the strange chemistry of Titan, becoming part of the world it had briefly visited? These are decisions that have not been made, and that cannot be made until the colonists themselves are no longer in a position to participate in them. The fifth unanswered question, and perhaps the most consequential for the long term, is what kind of relationship humanity wants to have with worlds that harbor life. The Titan colony has set a precedent, but precedents can be followed or ignored, extended or reversed. Future generations will have to decide whether to expand the protections the colonists requested, applying them to every world where life is found, or whether to roll them back, prioritizing human expansion over preservation of alien ecosystems. The debate has begun, but it is far from resolved. There are voices arguing that the only ethical response to the discovery is to withdraw entirely from worlds with biospheres, leaving them undisturbed for as long as humanity exists. There are voices arguing the opposite, that humanity has a right and even a duty to understand other biospheres in detail, even if that understanding requires some level of intervention. There are voices arguing for a middle path, in which limited research is allowed but settlement is prohibited. The arguments are passionate and the stakes are high, and the outcome will shape humanity's relationship with the cosmos for centuries. The sixth unanswered question concerns the future of the colonists' work. Even within the constraints they have set for themselves, they continue to gather data. They continue to map the surface, sample the chemistry, monitor the subsurface activity through every instrument they have. They will spend the rest of their lives doing this work, transmitting their findings back to Earth, contributing to a body of knowledge that will outlast them. But what becomes of that work after they are gone? Without follow-on missions, the data stream ends. Whatever Titan does in the centuries after the colonists' deaths will go unrecorded by human observers. The biosphere they discovered will continue its slow, patient work, but humanity will not be watching. This is a strange thought. We will know that life exists on Titan, but we will not be in active relationship with it. We will have made contact, in a sense, and then withdrawn. The implications of this kind of relationship, in which we acknowledge the existence of another biosphere, but do not study it actively, are something humanity will have to work out over generations. Beyond Titan, the next missions become a kind of test. If humanity chooses to send probes to Europa or Enceladus, what will those probes look like? Will they be designed for minimal contamination, with sterilization protocols far more stringent than anything used on previous missions? Will they be designed to look but not touch, to observe without sampling? Will they be designed to interact with whatever biospheres they find in some controlled and careful way? These design choices will reflect the philosophical positions that humanity has settled on or failed to settle on in the decades following the Titan discovery. The probes themselves will be both scientific instruments and ethical statements, embodiments of how we have chosen to be in the solar system. The questions accumulate faster than they can be answered, and the colonists, growing older in their habitat, watching the orange sky day after day, understand that they have begun something that they will not see completed. The work they have started will take generations. The decisions they have requested will be made by people who have not yet been born. The future they have helped to shape will unfold long after their voices have fallen silent across the long communication gap. They will die in the twilight of a world that has accepted them in their small numbers, but that does not need them. And what comes next is for others to decide. There is a kind of silence that settles in when you sit with everything that has been said about Titan, about the colony, about the discovery of life, and the decisions it has forced upon us. It is not the silence of vacuum, or even the soft, rustling silence of Titan's thick atmosphere. It is the silence that comes after a long conversation about something enormous, when the words run out, and what remains is the simple weight of what has been understood. And what has been understood, in the long arc of this story, is something that humanity has been circling for centuries without ever fully facing. We are not the center of the universe. We have known this, intellectually, since Copernicus. We have known it more concretely with every telescope, every probe, every photograph from deep space that revealed the immensity of what surrounds us. But knowing it intellectually is not the same as living with it. For most of our history, even as we expanded our understanding of the cosmos, we have continued to behave as if the story we were telling was, fundamentally, our story. The universe was the setting. We were the protagonists. The stars and planets were the backdrop against which the drama of human civilization would unfold. Even as we sent probes to other worlds, even as we discovered the vast scale of the galaxy and the universe beyond it, we maintained, deep in our cultural assumptions, the idea that we were the ones who mattered. The Titan discovery, when it comes, does not refute this assumption in any direct way. It simply makes it impossible to sustain. We are not the only producers of life in our own solar system. We are one expression of a phenomenon that happens elsewhere, under different conditions, with different chemistry, producing different outcomes. The universe is doing what it does. We are part of it, not separate from it. And whatever significance we have is not because we are unique, but because we are aware. We can ask the questions. We can hold the wonder. We can recognize, when we encounter it, that something other than us has been doing its own slow, patient work for ages before we arrived. This recognition is, in some ways, the deepest gift the Titan colonists give to humanity, though they do not realize they are giving it. By going there, by being willing to leave Earth forever, by encountering what they encountered and responding to it with the integrity they showed, they make it possible for the rest of us to grasp something we could not have grasped from Earth alone. They make the cosmos personal in a way it had not been before. They become the bridge between the abstract knowledge that life might exist elsewhere and the concrete reality that it does. And that bridge, once built, cannot be unbuilt. We cannot return to the universe we lived in before the discovery. We can only live in the universe as it actually is, and figure out, slowly, what that means for who we are and how we should behave. What strikes me, sitting with all of this, is how small we are and how large the implications are at the same time. We are a single species, on a single planet, in a single solar system, in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. The numbers are so vast that they lose meaning when you try to hold them in your mind. And yet, within that vastness, we have done something extraordinary. We have become aware. We have begun to ask the questions that the universe itself, in all its immensity, cannot ask without us. The stars do not wonder about themselves. The galaxies do not contemplate their own existence. Only beings like us, fragile and brief and embedded in matter, can hold the universe up to itself and try to understand what it is. This is not, in the cosmic sense, a particularly important thing. The universe will continue to exist whether we understand it or not. But it is, for us, the thing that gives our existence its meaning. We are the part of the universe that asks, and the Titan discovery has expanded what we can ask. We can now ask whether the other parts of the universe are also asking, in their own ways, in their own chemistries, in their own slow, patient processes that we have only begun to detect. The Titan colonists, in their last years, write about this often. They describe what it feels like to stand under that orange sky, knowing that beneath their feet, in the deep ocean that they will never reach, an entirely separate experiment in chemistry has been running for hundreds of millions of years. They describe the strange peace that comes from understanding that they are not the most important thing on the world they inhabit. They describe the way the cold and the orange light and the patient, slow rhythms of Titan have begun to feel like home, not in the sense of comfort, but in the sense of belonging. They are still human. They are still earth creatures in their hearts and in their longings, but they have made their peace with where they are and what that means and what they will leave behind. When the last of them dies, eventually, in a habitat that has been their home for decades, the rest of humanity will mark the moment in some way. There will be ceremonies. There will be statements. There will probably be debates about what to do next, about whether to send another mission, about what kind of relationship to maintain with the world they had made their home. But the colonists themselves will not participate in any of that. They will simply be gone, their bodies preserved in the eternal cold, their habitats slowly absorbing into the strange chemistry of Titan, their voices silent at last across the long communication gap that had defined their lives. And Titan will continue. The orange sky will continue. The methane will fall, and the rivers will flow, and the dunes will shift, and the deep ocean far below will continue its slow, patient work, undisturbed by the brief presence of 7 humans who passed through and left their mark and then were gone. This is, in some sense, the truest cosmic perspective we can hold. We are temporary. The universe is not. We are aware. The universe, for the most part, is not. But the universe produces awareness, in places and in forms we are only beginning to discover. We are one of those places. Titan, possibly, is another, though in a form so different from ours that we cannot easily recognize it. The galaxy is probably full of others. We will never meet most of them. We will never know what they think or feel or experience if those words apply at all. But they are there, doing their own work, being their own kind of expressions of whatever the universe is doing when it produces life and awareness. And we are not alone, in the deepest sense, even though we are alone in every practical sense. The loneliness and the not being alone exist together, side by side, and we have to learn to hold both at once. The colonists, in their orange twilight, have learned to hold both. They are alone in a way no humans have ever been alone before, separated from everyone they ever knew by a gap of light minutes that no message can cross quickly enough to matter. And they are not alone, because beneath their feet, in the deep ocean far below, something else is alive, and has been alive since long before their species existed. They live in that paradox every day. They have made their peace with it. And in their slow, careful transmissions back to Earth, in the years they have left, they tell us, again and again, that the paradox is not something to be solved. It is something to be inhabited. It is the truth of our situation, here at this strange moment in the history of awareness, and the only response that does justice to it is to accept it and to live well within it. Tonight, we have traveled together to a place that does not yet exist, a colony on a moon nearly 1 billion miles from home, and we have asked what it might mean for humans to live there and what it might cost them to stay. We have walked across the icy ground beneath an orange sky. We have stood at the edge of methane lakes and looked up at a sun that appears no brighter than a full moon. We have considered the propulsion technologies that would carry us, the life support systems that would sustain us, the radiation environment that would shape our bodies, the slow, corrosive weight of separation that would shape our minds. We have followed 7 imagined colonists from their arrival to their final years, watching them discover that the world they had come to settle was already inhabited, watching them make the decision to ask that no one else be sent, watching them live out their lives as the first and last of their kind. And we have tried, in the only way that words allow, to understand what such a choice would mean. What I want to say, as we come to the end of this long exploration, is that the story we have told tonight is not a prediction. It is not a forecast. We do not know whether life exists on Titan. We do not know whether humans will ever travel there in significant numbers. We do not know whether the political and economic conditions that would make such a mission possible will ever align. The future is open in ways that no story can capture. But what we have done tonight, in walking through the possibilities together, is something different from prediction. We have rehearsed a question that humanity may one day face for real, and we have tried to feel its weight before we have to bear it. This is, in its own quiet way, an act of preparation, not for the specific mission to Titan, which may never happen, but for the larger question of how we want to be in the cosmos, what we owe to other worlds, what we owe to ourselves, what it means to expand, or to choose not to expand, in a universe that turns out to be more populated and more strange than we had imagined. The reason Titan colonization, if it ever happens, would be the most painful decision humanity has ever made is not because of the engineering challenges. The propulsion problems can be solved. The life support systems can be built. The habitats can be designed. The cold can be insulated against. The radiation can be shielded by Titan's own thick atmosphere. The technical obstacles, while immense, are within the reach of a civilization willing to commit the resources. The pain is not in the engineering. The pain is in the choosing. To send humans to Titan is to send them across a gap that no message can cross quickly. It is to commit them to a separation more complete than any humans have ever endured. It is to ask them to live in a place that may turn out to be inhabited by something we did not know was there, and to figure out, in real time and at the edge of the solar system, how to be in relationship with that something. The pain is the moral and existential weight of the decision, not the physical difficulty of carrying it out. And yet, despite the pain, the case for going does not entirely disappear, because the universe is what it is. The future is long. Earth is fragile. The dream of becoming a species that exists in more than one place is not, by itself, a bad dream. It is the way that dream has often been articulated, as conquest, as expansion, as the imposition of human presence on whatever worlds happen to be there, that needs to be re-examined. Titan, in this story, becomes the world that forces the re-examination. It teaches us that the universe was not waiting empty for us to fill it. It teaches us that the right way to be in the cosmos is not the way of the colonist in the old sense, but something more careful, more attentive, more humble. The first humans to live on Titan in this imagined future become the ones who teach us what that means. They go expecting to conquer. They stay as witnesses. They die as protectors of something they did not know they would find. And their legacy, more than any flag they planted or any infrastructure they built, is the lesson they leave for the generations that follow. What I hope, more than anything, is that this story has done something for you tonight that has nothing to do with Titan specifically. I hope it has reminded you that the universe is larger and stranger than the daily concerns of our lives usually allow us to remember. I hope it has reminded you that life, including your own, is part of a phenomenon that extends far beyond what we can see from any single planet. I hope it has reminded you that the questions we ask about our future, about our place in the cosmos, about what we owe to one another, and to whatever else might be out there, are not abstract philosophical puzzles. They are the real questions of our time, and they will become more urgent, not less, as our capabilities grow. The Titan story is one way of approaching those questions. There are others, but the questions are real, and they will not go away because we choose not to face them. The colonists in this story, the 7 imagined humans who lived and died beneath an orange sky, are not heroes in the simple sense. They are not villains either. They are people who made the best decisions they could in circumstances that no one had prepared them for. They did not solve the problems they encountered. They identified them, articulated them, transmitted them back across the long gap to Earth, and left them for the rest of us to work out. This is, in some sense, all that any of us can do. We are each of us small, brief, embedded in our own particular places and times. We cannot solve the long questions of our species. We can only contribute, in our own small ways, to the slow, ongoing conversation that humanity has been having with itself for millennia about what we are and where we are going. The colonists contribute by going. We contribute, perhaps, by listening, by thinking, by sitting with the questions long enough to let them shape us. So that is what I hope you will take from tonight. Not a prediction, not a plan. Just a question, held in the mind for a while, allowed to do its slow, patient work. What kind of cosmic citizens do we want to be? What do we owe to the worlds we have not yet visited? What do we owe to the futures we will not live to see? These questions do not have easy answers. They may not have answers at all in any final sense, but they are worth holding. They are worth carrying with us into our ordinary days, into the small decisions that make up our lives. Because the small decisions are where the larger answers, eventually, get written. Thank you for staying with me through this long journey across the solar system and back. If anything we explored tonight has stayed with you, if any image or idea has lodged itself somewhere in your mind to be turned over later, then the time was well spent. If you would like to keep traveling with us into other strange and distant places, into the cold edges of our cosmic neighborhood and beyond, take a moment to like this video, leave a comment, and subscribe to the channel. Tell us, in the comments below, what country you are watching from, and what part of tonight's story struck you most deeply. Share this video with someone who needs to think about something larger than the daily news. And if this kind of slow, careful exploration of space and the future is the sort of company you want for your quiet evenings, you can find more of it here whenever you need it. The orange sky is waiting. The future is open. And we are, all of us together, still figuring out who we want to be when we finally get there. Good night, and thank you for traveling with me.